Today our speaker is Mark Harris. He is our CUDA technologist and serves as both a developer advocate and also helps us to figure out what the future generations of the CUDA platform are going to include. Today Mark's going to share with us some information about the current CUDA 6 release and the next several releases, CUDA 6 and beyond. So Mark, please take it away.
Thanks, Will. Welcome, everyone. Thanks for coming. As Will said, I'm going to talk about CUDA 6 for about 2/3 of the presentation and then give a little taste of beyond. So I'm going to show you 4 main features of CUDA 6 this afternoon, starting with unified memory. And then I'll talk about CUDA on Tegra K1. And then I'll talk about our extended interface libraries and drop-in libraries that are new in CUDA 6. And then finally, show you some improvements to developer tools. The goal of unified memory in CUDA 6 is to dramatically lower effort that developers put into writing code for CUDA. Today, this is what the developer sees when they go to write code for GPUs. It's a heterogeneous system, and the programmer has to explicitly manage data for the distinct memories of the 2 processors, the CPU and the GPU. And the developer has to explicitly copy data between the memory spaces if they want to share the data between GPU code and CPU code. And that results in fairly complicated code. Unified memory provides developers with a managed memory pool that gives them a single view of their data, and the runtime takes care of migrating data to the processor that accesses it behind the scenes, so that mem copies, where they used to be a requirement, now become an optimization. The result is greatly simplified memory management code, as shown here. The code on the left and the right do the same thing. They basically both allocate data, allocate memory, copy data from a file into the array that was allocated, and then sort the data using a QSort routine, quicksort. And then they use the data in some other way on the CPU before freeing the memory. The code on the right is CUDA 6 code with unified memory. And the main differences are that in order to allocate memory in the unified space, we just use CUDA malloc managed rather than malloc. And that gives us a pointer that we can pass to CPU functions, like we pass it to fread initially to load the data into the file. And we can also pass the pointer to kernels, like the QSort kernel that you see there with the familiar triple angle brackets of CUDA. And then after the GPU kernel is done using the data, we can pass the same pointer to another CPU function, this useData function, as long as we're careful to synchronize so that we don't access the data that's still in use on the GPU. And then to free the data, we just use CUDA free instead of standard free. And so this is much simpler than pre-CUDA 6 code, where you had to allocate on the CPU and do another allocation on the GPU and then do a mem copy to the GPU before calling the kernel and a mem copy back before you wanted to access data on the CPU. So unified memory delivers in 2 main areas. The first is a simpler programming and memory model. You get a single pointer to your data that you can access from either processor, CPU or GPU, and even from multiple GPUs in your system. And that gives you tighter language integration, so it becomes much simpler to share data between the CPU and GPU, but also, as I'll show you later, it's much simpler to share complex data structures between the CPU and GPU because it eliminates the deep copy problem that you have today. And the second area is performance through data locality. So because we migrate the data to the processor that's accessing it, we make sure that when the data is accessed by that processor, it gets the full bandwidth of its memory, rather than, for example, accessing data all the way in CPU memory from the GPU, which would limit you to PCI Express memory bandwidth. We also guarantee global coherence. Today, that happens at the point of kernel launches and at synchronization, either of the device or the stream. And you still have access to all the tools you had before, the APIs for asynchronous mem copies, like CUDA memcopy async, for optimizing performance. So you can still, once you have your application working, if you need to make sure that you get the most performance, you can use asynchronous mem copies to overlap compute and copies. So let me give you an example of one of the problems this helps solve. Today in CUDA code, yesterday in CUDA code, before we had unified memory, if you have complex data structures that contain pointers, for example, this structure here, this data elem struct, has 2 int members and a char star, so it's a pointer to some text. And in our example, we have this structure allocated in CPU memory, and it points to a string, in this case, hello world. If we'd like to pass that to a CUDA kernel and access that data on the GPU, then that requires 2 copies. It's what we call a deep copy. So we have to copy the struct itself, but also the data it points to. And if that structure nests deeper, if you have pointers to other pointers, then of course we have to follow those pointers and do more copies. And so the result is quite complicated code just to call this kernel that accesses this fairly simple struct. In this example here, you can see we have 2 CUDA malloc calls to allocate the struct and the string on the GPU. But then to copy it, it takes not 1, but not 2, but 3 copies. The first one to copy the structure, the second one to copy the string, and the third one to copy the address of the string into the pointer in the structure, so that it's no longer pointing back to the host. And only then can we launch the kernel, which uses the struct on the GPU. But with unified memory, all we do is make sure we use CUDA malloc managed to allocate the struct and the string, and now we can just launch the kernel and pass it the structure directly, and it just works. It's really important that our developer tools are usable on every new feature that we have. So I'm happy to say that in CUDA 6, all of our developer tools support unified memory. So this is profiling and debugging tools. The visual profiler, you can see on the timeline, along with your kernel calls and your CUDA mem copies, you can see the migrations of data and the CPU page faults that happen along the timeline. Also in NVProf, it's not shown here, NVProf is our command line profiler. You're able to capture the unified memory statistics in the same way. You can visualize them in text format, or you can import them into the visual profiler. CUDA memcheck is able to tell you when, of course, when you access out of bounds, just like in regular device memory. It can do the same for unified memory. It can also tell you when you dereference unified memory from the host at illegal points. For example, if a kernel's still running with that's accessing unified memory, then CUDA memcheck will tell you that the host has caused a fault by accessing the same memory. CUDA GDB also will show you those faults while you're debugging. Unified memory becomes really powerful when you combine it with features of C++ for object-oriented programming. Today, I mean, before unified memory, it's difficult to integrate C++ object-oriented data structures between CPU and GPU code. The reason is that the CPU can't construct GPU classes in GPU memory, and you can't pass by reference because the reference is to a CPU structure, and so that will fail unless you happen to be using mapped memory for that. So that makes it difficult. But with unified memory, we can use features of the language to make this a lot more manageable. So here I've created a class called managed, and I'm using the fact that in C++ you can overload the new and delete operators. And of course, I could do this outside of class. I could overload them globally, but then everything would be unified. But inside the class, I overload the new operator to use CUDA malloc managed rather than malloc. And I overload the delete operator to use CUDA free rather than free. And that means that I can create my data element. Sorry, I'm getting ahead of myself. I can create a class and inherit from that. So in this case, I've got a string class that inherits from managed. And as a result, if I say new string, then it's automatically created in unified memory. And that means that we can already use this for pass by reference, because references will point to unified memory, which both the CPU and the GPU can access. And if we also change our copy constructor for the string class to use CUDA malloc managed, then now we get pass by value working. So now I can pass a structure by value, which causes the copy constructor to be invoked, which will create a copy of the string in unified memory, and then the kernel can access it also. And so now in my data element class, if I use a string, this string class instead of a char star, and the data element is also managed, so by inheriting from the managed base class, then now I have a concise and explicit way to let C++ handle my deep copies for me. And it enables both pass by value and pass by reference for data structures when calling kernels. So here I've got an example of pass by reference. Here you can see on the bottom in the GPU program is called kernel by ref, and it takes a reference parameter. You may know that before CUDA 6, this was illegal. We couldn't pass by reference to kernel launches. And so now reference parameters are enabled as long as they point to GPU accessible memory, aka unified memory or device memory. Now when I call this kernel, it passes the value, the struct by reference, so it doesn't need to make a copy, but the reference points to the unified memory object, so this just works. And another example, pass by value. Here, instead of the reference parameter, I just have a pass by value parameter, and this causes the copy constructor to be invoked. So I get a new copy, but it's still in unified memory, and so that works too. So the nice thing about unified memory in CUDA 6 is that we have a roadmap for further improvements. With CUDA 6, we focus on ease of use. So you get a single pointer to data. Memcopy becomes more of an optimization rather than a requirement. It gives you coherence at the point of kernel launch and at synchronization. And as I showed you, it enables sharing complex C and C++ data structures between CPU code and GPU code. In the next releases of CUDA, we plan to focus on performance a bit more with some optimizations. For example, we might be able to do prefetching on the CPU when the CPU is striding through data in a predictable manner. And migration hints, such as when you allocate unified memory, you might specify that this data is read-only from one processor or the other, which might help the runtime decide better when to migrate it or not migrate it. And also, we'll be expanding platform support to more operating systems, more platforms. Today, we have 64-bit Linux and Windows support for unified memory. And on the Tegra K1, it's supported in 32-bit Linux. In future GPUs that have hardware support for unified memory, this will give us the ability to do finer grain migration. So it's not just the whole, the whole allocation isn't migrated today, but you'll be able to access potentially parts of an allocation on the CPU while other parts are being used on the GPU. And you won't be limited to allocating memory that's smaller than the size of the physical GPU memory, so that you can oversubscribe GPU memory and solve problems that don't fit. If you'd like to learn more details about unified memory, there's a blog post you can check out on the Parallel for All blog with the URL shown there. Okay, next I'd like to tell you about CUDA on Tegra K1. Hopefully most of you went to the keynote this morning. Jensen gave a great keynote, and one of the exciting things that he talked about was Tegra K1 and the JETSON TK1 platform, which is, he called it the world's first embedded supercomputer. It's intended to be a development platform for mobile embedded computing. So applications like computer vision and robotics, for example. It includes the Tegra K1 system on a chip, which is a CUDA-capable, has a CUDA-capable GPU. And it'll be $192, so it's quite an affordable development platform, whether you're a scientist or a researcher, an engineer, or a hobbyist. And it's available for pre-order now. If you want to see more, stay in this room after my talk. Jesse Clayton's going to do a JETSON TK1 unboxing and tell you more about the platform. And if you want to try it hands-on, we have hands-on labs in room 230B on Thursday. Yeah, Thursday at 2 and 3:30. So the intent of providing this kind of development platform is that we have this new processor with CUDA capability, and we know that CUDA is great for a wide variety of parallel applications. And we think that the small form factor gives developers who want to do interesting new things an opportunity. So things like computer vision and robotics, or automotive applications, medical devices, and avionics. So I know the avionics guys like to joke that their physical constraints are 0 weight, 0 power, and 0 size. So we didn't quite get there with JETSON TK1, but hopefully it's something they can start with. A little bit more detail about Tegra K1. Again, it has an Nvidia Kepler GPU. It's our first system on a chip, our first Tegra processor with a Kepler GPU, or with a CUDA-capable GPU. So we really do have CUDA available everywhere now, top to bottom, across our products. It has a quad-core A15 CPU, and the GPU is a single Kepler SM with 192 CUDA cores. In case you're curious, that's compute capability 3.2, which basically has everything that a desktop Kepler has, except for CUDA dynamic parallelism. But I'm sure that'll come in the future. And it's capable of over 300 gigaflops. CUDA 6 is supported. The CUDA toolkit 6.0 is fully supported on Tegra K1. And so you'll be able to download that and use it on the JETSON to develop applications. Tegra supports unified memory. The difference from desktop is that on Tegra, since it's a system on a chip, the memory is physically unified. And so there aren't separate CPU and GPU memories. However, the caches are still separate. And so to use unified memory, that just basically means that you use the same programming model as on desktop. You use CUDA malloc managed, and you get coherence at launch and sync. Another great feature of Tegra is that it doesn't just support OpenGL ES, the embedded OpenGL, but it supports full desktop OpenGL 4.4 and DirectX 11, which means that if you have existing software that does compute and graphics, then it's quite easy to port it over and get it running. Modulo performance, of course. And because the JETSON TK1 runs 32-bit Ubuntu 13.04, which is a modified Ubuntu that we call Linux for Tegra, or L4T, existing Linux software is even easier to port. The third main feature I want to talk about is XT and drop-in libraries. So as you know, we have CUBLAS and CUFFT are kind of the oldest libraries in the CUDA toolkit. They're the first ones that we created. And in CUDA 6, they're getting a major new feature, which is these extended library interfaces. And these enable automatic scaling across multiple GPUs in a single machine, in a single node. So that's for 2D and 3D FFTs and BLAS level 3 operations. So for example, matrix multiply. So this graph shows scaling, obviously. We have a 16K by 16K SGEM operation, so single precision matrix multiply, running on K10, which is a dual GK104 board. That's a Tesla board. And GK104 is optimized for single precision. That's why we're showing that here. But it scales, each board's 2, so we go from 2 GPUs, 4 GPUs, 2, 4, 6, 8 GPUs, and go from 2 teraflops up to almost 8 teraflops. Another great feature of XT libraries is that they allow you to operate directly on large data sets in system memory. So if you have matrices that are too big to fit in the GPU memory, then you can still multiply them and still scale across multiple GPUs. And the reason for that is because matrix multiply is so compute bound that we can tile it up and overlap transfers and compute to completely hide the transfers. And so you still get perfect scaling. We also are introducing a new library called NVBLAS, which is a drop-in replacement for CPU-only BLAS. So NVBLAS automatically routes BLAS3 calls to cuBLAS and passes through the smaller calls, the non-BLAS3 calls, to the user-specified host BLAS. And this is all configurable through a configuration file. So it's drop-in because in some cases, you can use it without even recompiling or relinking your application. So in this example we show here, on Linux, we're able to use the LD preload environment variable to specify a path to a library, which will be loaded before other libraries that are linked to the application. And so we LD preload libnvblas.so and then run R, the statistical package and language. And we use it to randomize two 2D matrices and multiply them, and then we time that for a range of matrix sizes. And you can see that it scales pretty well up to, this is showing up to 4 K20X GPUs compared to MKL. And you can use that approach on Linux in any application that uses standard BLAS3. So that could be Scilab or Octave, for example. On Windows, you would have to relink. So you'd have to redo your link phase and link NVBLAS before your other BLAS libraries. Okay, the last CUDA 6 feature I want to talk about is improvements to developer tools. But this is definitely not least, so last but not least, because developer tools are crucial for making our platform accessible and usable by developers. And so we invest pretty heavily in these. And we have some cool new features. Probably the one I think has the biggest impact is this one, which is remote development with Nsight Eclipse Edition. What this enables you to do is use a local IDE on your desktop for development of an application that's running remotely. So in a lot of cases, in CUDA, you might be running your application on a server or a cluster or on a Tegra development kit that you're connected to via SSH. And so Nsight Eclipse Edition has built in the ability to manage connections to remote machines and to find or to specify the location of the CUDA toolkit on those machines so that you can edit locally and get all the benefits of the IDE's editor like CUDA aware syntax highlighting and things like that, and then build and run remotely with automatic synchronization via SSH. And if you're developing for ARM, for example, for JETSON, you can compile locally using cross-compilation to ARM and then run remotely. Of course, this gives you all the features of Nsight Eclipse Edition, including full debugging of your GPU code and CPU code, as well as profiling over the remote connection. So this is pretty powerful. Another feature that we introduced in CUDA 5.5 was MPS, which stands for multi-process server. The intention of MPS is to enable better scaling in MPI applications on clusters, where each rank or process of the MPI program is not able to completely fill a GPU by itself. And so MPS allows multiple MPI ranks to run their kernels on one GPU. So you can run multiple ranks per node, and they'll all use the same GPU and get better scaling because you're getting better utilization of your hardware. But in 5.5, we didn't have any tools that supported MPS. With CUDA 6, we're adding profiling support via NVProf, which again is our command line profiler. And so you can run NVProf on the cluster where the MPI program is running and capture traces, which you can then import into the NVIDIA Visual Profiler. And then you'll get a view like shown here where you can see the timeline for each process together so that you can see how they're, where any stalls are and how efficient they're running. CUDA memcheck is another tool. This is a command line tool that allows you to check for out of bounds or misaligned memory accesses, as well as race conditions and memory leaks in CUDA code. And CUDA memcheck can now be used on applications running MPS. So that's good because when you have these big, complicated MPI cluster codes, being able to find your memory bugs is very important. Pardon me. The profiler has a new feature, actually several new features, but I only have time to cover a couple of them, related to more detailed kernel profiling. So this is one of them. It's visualization of a detailed instruction mix. So we can see the breakdown of the instructions in terms of what percentage of them were floating point, integer, control flow, et cetera. And we can even dig deeper and see of the floating point, how many were adds, how many were multiplies, multiply adds, et cetera. And that's helpful if, for example, you might see a case where you should be mostly doing floating point operations, but you've got a high integer operation count. And maybe that's loop overhead, and loop unrolling might help reduce that, for example. And then another detailed profiling feature is kernel profiling with instruction counts. So here the profiler can run your kernel and capture counters per each instruction in the kernel, and then show you in your code, as long as you compile with line info. And on each line of code, you can see a number to the left of it, and that's the number of instructions that were executed total for the kernel at that line of code. And then you see in the exploded view on the right the lines of, or the assembly instructions that correspond to that line of code, and they each have individual counts also. So that's very helpful for giving you potential hotspots in your code because you can see which lines of code are run most. So in this example, we have a convolution kernel, a separable convolution kernel, and the inner loop, of course, is executed most, which is as expected in this case. It'll also show you potential inefficient locations in your code. If you look up at line 77, there's a little blue bar, which is kind of a little bar graph, which if it's empty, then that means all the threads executed that line of code. And if it's partially filled, then that means that some instructions were not active. Some threads were not active at that line of code. And so you can get an idea of the divergence in your code. If you're interested in learning more about Nsight Eclipse Edition and other tools, there's several talks. I wanted to highlight just this one here, which is called CUDA Application Development using Nsight Eclipse Edition. It goes into a lot more detail about the tools than I'm able to in this talk, and they have some nice examples. So check it out. So that's CUDA 6. I think that unified memory is one of the most important features we've introduced in all versions of CUDA. So I'm pretty excited about that. So please try it out. The release candidate is available now for download, and the official release will be out pretty soon. The URL's there. It's basically developer.nvidia.com, CUDA toolkit. So now I want to take a little bit of a look forward and talk about our goals and our process and some of the directions we're investing in for the future of CUDA. It's creating a vision and a direction for a platform like CUDA is not an easy task. And I work together with a great group of engineers inside NVIDIA on this. And we've got the needs of many customers and developers that we want to address, as well as some of our own internal goals. And we are constantly having to balance priorities and try to make sure that we focus on the directions that are going to be the most valuable to users of the platform going forward. And so we have a set of goals that we think about. And increasingly, these top 3 goals here are becoming the most important. So simplicity is really important in the platform because we want it to be really easy to learn parallel programming in CUDA, as well as to adopt it into existing applications as well as new applications. And related to that is productivity. Every programmer, every developer has goals for both features as well as performance of their application. And so we need to make it possible to achieve those goals quickly, as well as provide tools and capabilities that allow developers to recognize the barriers that are keeping them achieving their goals and potentially how to overcome those barriers. So that's why we invest in things to simplify programming like unified memory, as well as we invest heavily in our developer tools to help developers find problems quickly and fix them. Portability is increasingly important. Developers always need to run their code on multiple platforms. Well, not always, but often. And portability has a lot of faces. So it can mean portability across our products. It can be portability to future GPUs, making sure that code that's written today will run well on future products. But it can also mean the ability to run your application across different architectures and different operating systems. And one of the ways that we're working hard on portability is by trying to make sure that parallel computing is accessible from mainstream languages. And I'll talk about that a bit more. And of course, performance is always important to CUDA. It's been important since day one, and it continues to be important. But not just absolute performance on the GPU, but also scalability of the application from smaller GPUs to larger GPUs, across multiple GPUs, and on clusters. What we'd like is to simplify heterogeneous application development. So today, we have the picture on the left, which is this kind of hybrid programming where you have explicit heterogeneous programming. You have explicit notions of CPU code and GPU code, CPU memory and GPU memory. But we'd like you to be able to write homogeneous programs that execute on heterogeneous systems. So we need a unified programming model that exposes parallelism in the language and that abstracts the scaling from small parallelism or no parallelism to large parallelism through features in the runtime and virtual machines. And so we're working on a number of programming model features and APIs and things like that for the future to try to achieve this. I mentioned before that if we want to enable more programmers to write parallel software, as well as to write software that they can reuse and port to other platforms or from other platforms, then we need to make sure that parallelism is accessible in mainstream programming languages. Programmers today, they like to have choice. You don't write applications usually just in one language. Often, even for a single project, developers use multiple programming languages. And so in the future, you're going to see support for parallel computing, for GPU computing in key programming languages. And I show the logos of several languages and parallel programming APIs here. And we're more or less, we're involved to greater or lesser extents in all of these, and we're making progress. And I have 4 of these that I have, progress updates on in this talk. So I'll tell you about those. Several years ago, our research team, NVIDIA Research, started working on parallel algorithms. And they created a library that you may have used called Thrust. It's a parallel C++ template library. And it provides a complete set of parallel primitives, such as for each, sort, scan, reductions. And it's very powerful and expressive for building up parallel algorithms from fairly high-level components. And also, it demonstrates the ability to use these high-level primitives to achieve performance portability because it's designed in a way that it can have backends for multiple architectures. And in fact, Thrust does have backends for OpenMP and threading building blocks as well as CUDA. I don't know, maybe a year and a half ago or so, Jared Hoberock, who's one of the main authors of Thrust, presented a paper to the ISO C++ committee about a proposal for a parallel algorithms library. And it was very well received. And so since then, they've written a technical specification, which in February was unanimously voted to be a official working draft technical specification within the ISO C++ committee. So that means that this is in the process to become part of a future standard, perhaps even C++ 17. So I think this is really exciting because it provides a standard way for programmers in C++ to write parallel programs that can provide portability, even potentially performance portability, and they can program at a fairly high level in the language they're familiar with. Another way to reach lots of programmers is by getting GPU accelerator support into open source compilers. So I'm excited about this collaboration. This is a collaboration between Samsung and Mentor Graphics. They're actually, they started independently, but they're both working in the same branch of the GNU compiler source tree. And they're working on adding OpenACC support to GCC. And so I think this is going to have a big impact because GCC is the most widely used HPC compiler. And so this has the potential to provide GPU computing capability to a lot of people. Another very popular language is Python. I think Python's popular because it's very high level and productive because it's got an expressive but very understandable syntax, and it has kind of a batteries included set of libraries, as well as very popular libraries like NumPy. And so Numba is a open source compiler for array-oriented Python that's sponsored by Continuum Analytics, and they do a lot of the work on it. Last year at this conference, I talked about Numba Pro, which is a product from Continuum that's similar but has more features. And what's new here is last week, Continuum contributed the CUDA Python portion of Numba Pro to the open source Numba source tree. And so now in the open source library, you have access to the CUDA programming model from Python syntax. So you can write code like this where I have this Saxby function, and by specifying a type signature, that allows the compiler at runtime, just in time, to compile a version of that for running on the GPU. And then I can launch it using a syntax similar to CUDA C, where I specify the grid dimensions and the block dimensions. So that's really exciting. You should check that out if you're a Python programmer. And then the fourth language I want to talk about is Java. But first I want to talk a little bit about an application of Java. In this case, it's GPU-accelerated Hadoop. Hadoop is a MapReduce framework that's used for large-scale data analytics. It allows you to scale programs across distributed computing systems. And Hadoop has a framework for machine learning called Mahout that IBM is demoing a GPU-accelerated application of in their booth here at GTC. And what they've done is developed a CUDA-accelerated IBM Java that allows them to do, in this case, k-means clustering, which is a common machine learning algorithm. And so, we have all this data on the internet. I think I heard someone say 2.5 exabytes a day are created or something by the internet, something crazy like that, or a year maybe. And it's tripling every 2 years or something like that, or doubling every 3 years, one of those. Anyway, companies, governments, researchers, they all want to find ways to use this data. And one of the ways they can do that, for example, companies can use clustering algorithms to segment their customers by large number of dimensions of data that would be impossible to process with more manual methods. And so this demo is just demonstrating this common k-means clustering algorithm running on Hadoop on Nvidia GPUs and IBM Power CPUs. So check that out. Nvidia also has a very nascent Java project inside our compiler group. This is a project that they're calling JOG for Java on GPU. It's a demonstration of an approach using or applying what's called a closure to a set of arrays. This closure is, you can think of it if you're a C++ programmer as a functor, a function object. It's a class with an execute method that is basically a function call operator. And JOG provides a for each method that applies the parallelizes the closure's execute method over the GPU threads. And so they have some preliminary results. The graph is a Black-Scholes options pricing code comparing a single GK104 GPU to sequential Java code. And they get over a 12x speed up. If you want to learn more about that, then go to Vinod Grover's talk on Wednesday afternoon, 5:30, called Accelerating Java on GPUs. Another area that's really important for us to invest in is in improving cross-cluster communication. If you're scaling an application over a large cluster, then as you divide up the computation I'm talking about strong scaling here, where the the computation size stays the same and the cluster grows. Then you're dicing it into smaller and smaller bits, and so the latency of communication between each node becomes really important. And so we have a technology called GPUDirect RDMA, which, starting with CUDA 6, is now available in OpenMPI and NVBLAS 2. And the graph on the left shows reduction in internode latency using NVBLAS 2. And the result of that is better application scaling. So on the right, we see Humdi Blue from the University of Michigan scaling without GPUDirect RDMA and with it. And you can see they get twice the performance on 96 nodes with GPUDirect RDMA. It's also important when we have these low-level technologies to make sure that they're accessible to developers from the high-level APIs. And so we're starting to get involved in the MPI standards organizations as well as other standards like OpenSHMEM to make sure that in the future programmers have access to any high-performance communications technologies that we create. And I just want to finish by talking about some of the things that you probably saw in the keynote today and how they will impact you as a developer. Jensen talked about the new Pascal architecture, the future Pascal architecture, and two main features that will enable HPC on Pascal. And those are stacked memory and NVLink, a new NVIDIA-designed interconnect. As we move towards building exascale systems, it's really important to be able to feed the computational throughput of our GPUs with higher memory bandwidth and larger memories. So stacked memory brings the memory on the package with the GPU, giving us much higher capacity, much higher bandwidth, and much greater power efficiency. And the end result is that for developers, that means you can operate on larger working sets closer and faster to the GPU, meaning that you reduce the amount and frequency of off-package communication. So that can help reduce the PCI Express bottleneck or the interconnect bottleneck. And the other technology, NVLink, is intended to help with the interconnect bottleneck between GPUs and between GPUs and CPUs. And NVLink is PCI Express is a very thin straw for the GPU to get data through. So NVLink intends to make that straw much bigger. In fact, it should give the GPU access to data in CPU memory with bandwidth at least as high as the CPU's own bandwidth. And when you combine that with unified memory, that means you now have a single allocation of your data, and it doesn't matter so much where the data is. The cost, the access performance is just as high from the GPU if it's in CPU memory as it is from the CPU. And so that means your code gets faster and also simpler. And so I think this combination of NVLink and unified memory is probably the most exciting thing that's happened to CUDA programming in a long time. So I'm really excited for the future this will enable. OK, so that's CUDA 6 and beyond. I'm happy to take questions if we have time. I just want to pop up these talks that I had advertised earlier just so you can look at them if you want to go see them.